All right, let's do a problem here, ladies and gentlemen, involving a Carnot heat engine. So we got a Carnot heat engine with air is the working fluid. Air is what's inside the piston cylinder device. So we do a little schematic here. We have our piston cylinder device. Here's our piston. And the working fluid inside of the Carnot heat engine, our piston cylinder device, is going to be air. Okay? So air is the working fluid. It could be H2O, could be water vapor, it could be using some kind of other material, nitrogen, carbon dioxide. We're going to be using air as our working fluid. The heat received from the low temperature reservoir is 3.4 kilojoules. So let's put up a little picture here. Here's our high temperature reservoir. Here's our low temperature reservoir. Here's our Carnot heat engine. Carnot heat engine. It is rejecting heat to the low temperature reservoir, QL, and that's equal to 3.4 kilojoules. So we know that. Of course, it receives energy from the high temperature reservoir to produce a certain amount of work. If you like, work over the cycle. Work over the cycle. I'm going to put a subscript cycle there. You probably should do that too. So it receives it rejects 3.4 kilojoules to the low temperature reservoir. The low and high temperature reservoir temperatures are 300 and 250 degrees K. So this is 300 degrees Kelvin, and this is 250 degrees Kelvin. So T low, 250 degrees Kelvin, okay? The ratio of specific heats is going to be constant. Cp over Cv is going to be held constant. In other words, we're doing a constant specific heat analysis. The ratio Cp over Cv is always called K. The ratio of Cp over Cv is called K, and that's going to be given to you as 1.4. So we're going to do a constant specific heat problem. Many problems can be done using the ratio of specific heats without knowing what the actual value of the specific heats are. Okay, and you'll see this in just a little bit. Okay, mass for the air. The working fluid, 0.1 kilograms. The minimum and maximum volume in the cycle. Minimum and maximum volume in the cycle. 0.01 cubic meters, 0.0254 cubic meters. So let's put up the TV diagram. You should always put up a TV diagram when you do these kinds of cycle problems. TV diagram, some kind of diagram. So state 1 is the minimum volume, maximum temperature. 1 to 2, as you recall, for the Carnot cycle is isothermal heat addition from the high temperature reservoir. So the temperature here is T high, the air is at high temperature, T high, as we go from state 1 to state 2. Isothermal heat addition from the high temperature reservoir. Then we have adiabatic expansion down to T low. Adiabatic expansion down to T low. And then we have isothermal heat rejection to state 4. So we compress it. We compress the working fluid. Temperature is held constant. Why? Because heat's being rejected from the air as it gets squeezed down. And then we go back up to state 1 to complete the cycle with a adiabatic compressive process. Adiabatic compression process. So that's a cycle there. That's a cycle. All right, let's get started here. Let's get started. Let's calculate pressure at state 1. I think that's the easiest thing to do, so let's get started with pressure at state 1. Pressure at state 1. Well, I guess I can assume IGB. I'm going to do it. So if we assume ideal gas, it's pretty easy to calculate the pressure. Well, we'll see if it's easy. Hopefully it's easy. So analysis. I'm going to assume IGB. In fact, I'm going to write it in the assumptions in just a moment. But let me write down the ideal gas law. PV is equal to MRT. I can evaluate this at state 1. I want to know pressure at P at state 1. So I can solve this. P1 is equal to MRT1 over V1. Now, what are these pressures, temperatures, and volumes? What are these pressures, temperatures, and volumes? Or temperatures and volumes, sorry about that. Let's go back to our TV diagram and see if we can figure out what T1 and V1 are. Let's see here, T1 is equal to TH. That's the high temperature. What about V1? So what is this? Well, that's the minimum volume in the cycle. We're given the minimum volume in the cycle. So this guy here is Vmin. By the way, that's 0.01 meters cubed. So I know Vmin, or if you like V1. V1 equals Vmin. So I know this volume, V1, and I know the temperature, T1. It's T high. So this is M RT high over V min. Well, I know the mass, 0.1 kilograms. The gas constant for air is what? 0.286 kilojoule per kilogram degree in Kelvin. T high is 300 degrees Kelvin, and the minimum volume is 0.01 cubic meters. I'm going to get kilopascals out of that equation. I'm going to get kilopascals out. And I get 858 kilopascals. 858 kilopascals. 858 kPa. P1 equals 858 kPa. Okay, let's put a box around that. So that's the pressure. It's actually the maximum pressure in the cycle. We saw that from the PV diagram. So P1 is the maximum pressure, 858 kilopascals. Okay? Let's calculate the high temperature reservoir heat transfer, QH. Let's calculate the high temperature reservoir heat transfer, QH. In other words, Q what? In other words, Q1 to 2. Let's find out the heat transfer from state 1 to state 2. Okay, here. Process 1 to 2. This is isothermal. Isothermal heat addition. Isothermal heat addition from the high temperature reservoir. Now, if I write down the energy balance, let's just write it down. Well, let's write down the energy balance. I think that's the best way to go. So let's see here. Q1 to 2 minus W1 to 2 is equal to delta E, which is equal to delta U. Actually, I need to start doing some assumptions here. I was going to assume IGB, and also from that equation, I'm going to assume negligible changes in kinetic and potential energy. Let's do that right now. Assumptions. IGB And delta KE equals delta PE. No changes in kinetic and potential energy for any of the calculations over any of the processes, okay? Now we're working with constant specific heat. So this is mCV delta T from 1 to 2, okay? Delta T from 1 to 2. Now, if it's isothermal, what's delta T from 1 to 2? It's 0. 0, isothermal. So delta U is equal to 0. No change in internal energy because it's an isothermal constant temperature process. So what we get here, and by the way, Q1 to 2 is Q high. What we get is the heat transfer from the high temperature reservoir is equal to the work, 1 to 2. Now this is a piston cylinder device. I don't see any wires. I don't see any shafts in there. Carnot cycle didn't have anything to do with wires or shafts. So this is only boundary work. So this is boundary work. W bound. So that's going to be equal to the integral of PdV from V1 to V2. Now, it may not look promising at the moment. This is an isothermal process. It's not an isobaric process. It's not an isochoric process. It's an isothermal process. So pressure is a function of volume for an isothermal process. Let's see, from the ideal gas law, pressure is equal to mRT over V. That's from the ideal gas law. So let's put this in the integral. mRT over V dV from 1 to 2. Now this is an isothermal process. Temperature is at T high the whole time during the process. It's a constant. That means along with mRT, I can pull those things out of the integral. So I get mRT high integral dV over V from V1 to V2. The antiderivative of 1 over volume is a natural log. And so I get mRT high natural log V2 over V1. So that's the expression for my heat transfer from the high temperature reservoir. Now let me write this over in the corner here. Let me go write this in the corner. It's going to be an important relationship. Let me just write it right in the corner out of the way. Q high equals mRT high natural log V2 over V1. Okay? That's going to be our governing equation as far as calculating the heat transfer from the high temperature reservoir. Now let's take a look at this and see what we got, what we need to get, and what we already know. Let's see, I know the mass of the air. Of course, I know the gas constant is air. I know the high temperature reservoir temperature, TH. V1, in this case, this is V min. Okay, that's V min, but I don't know V2. V2 is some intermediate volume somewhere between V min and V max. Okay? V2 is somewhere in between. So this is V max. V3 is equal to V max, which I have, by the way. I've got this. And V2 is right here. Here's V min. It's some intermediate volume. I don't know what that is. Let's calculate V min. Let's figure out what, I'm sorry, let's calculate V2. Let's figure out what V2 is given our other information. Let's look at process. Okay, I want to know what V2 is so I can plug it in to get the high temperature heat transfer. Let's look at the process 2 to 3 because it will contain information about state 2. Process 2 to 3. And by the way, that is adiabatic expansion. That's adiabatic expansion. That's process 2 to 3. Well, let's write the energy balance down. Q 2 to 3 minus W 2 to 3 is equal to delta U, which is equal to mCV delta T from 2 to 3. Okay? Now, it's an adiabatic process, so this goes to 0. I know what the temperature difference is, delta T. And I know that the work is boundary work. So this is equal to the integral of PdV. And of course, pressure is a function of, according to the ideal gas law, a bunch of stuff. I'll have an M RT over V dV from V2 to V3, okay? Now, I'm kind of stuck at this point. I'm trying to get a volume V3, but volume's buried inside of this integral and temperature is not constant. 2 to 3 is not an isothermal process. 2 to 3, temperature's falling. It's changing during the process. I have no idea what temperature is doing at this point. So there's really no way for me to evaluate this integral or disentangle it to extract out V2 the way it stands. Okay? So I think I'm going to take a step backwards here. We're going to write another version of the energy balance. I'm going to write the differential version of the energy balance, differential process. Del Q minus del W is equal to dE, which is equal to du. Okay? That's a differential version of the energy balance. It's adiabatic. Adiabatic, so that goes away. And of course, the work is boundary work. So this is P dV. That's the boundary work. Okay? Now, if we assume constant specific heats, then du is equal to mCV dt. That's from the property relationship. du is equal to mCV dt. That's internal energy, not specific internal energy. Notice everything's capitals in here, all right? Okay, so let's write what I got. I got minus PdV is equal to mCV dt. All right. Now, what's pressure here? From the ideal gas law, pressure is equal to mRT over volume. That's from the ideal gas law, from IGB. Okay, so let me make the substitution here. M negative mRT over V equals, oh, I'm sorry, I forgot the dV, equals mCV dt. Notice the masses cancel out in that equation. That helps. And I get, let's write what I got. Let's write what I got left over. And I get negative RT over V equals CV dt. Oh, I forgot my dV in here. dV equals CV dt. Okay, that's from the energy balance differential form. I'm going to separate variables here and I'm going to integrate. I'm going to take all the temperatures and put them over on the right and leave the volumes on the left. Let's see what we get. Negative. I'm also going to put this R and put it over on the other side of the equation. So I got dV over volume. Keep the dV and the V and put the negative RT over on the other side of the equation. I have negative CV over R. Okay? And then I have dt over T. Let's integrate this over the process 2 to 3. So let's integrate this from volume V2 to volume V3. And let's integrate this. And let's integrate this from T1 to T2. The variable of integration is volume on the left, temperature on the right. Well, these are pretty easy integrals to evaluate. Notice that we're assuming constant specific heat, so the CV over R gets out of the integral, and I get natural logs. So I get natural log of V2 over V3 is equal to minus CV over R, natural log T3 over T2. Now let me take the CV over the R term and swallow it up into the natural log. Okay? And then I'm going to raise everything to the nth power. So I get T3 over T2 is equal to, V3 over V2. V3 over V2 is equal to T3 over T2 to the minus CV over R power. So for the adiabatic process, the ratio in volume is equal to the ratio in temperature to the negative CV over R. That's what that's saying. Now let's look at this equation here before we get too excited. I know T3 and I know T2. What are those? T3 and T2 are the low temperature and high temperature reservoir temperatures. So I know these temperatures. So T3 is T low and T2 is T high. Okay, so I know that. What about V3 or V2? Actually, I'm trying to get V2 here. So do I know V3? Well, let's have a look at our TV diagram here. So V3 is equal to V max. I already said I knew it. Yes, I know V3 as well. The only unknown in that equation is V2. And so in theory, I can solve for V2. So V3 is V max. Okay, V3 is V max. So let me solve for V2. V2 is equal to V3, which I know, times T3 over T2. Oops. I'm going to put this in parentheses here. Minus CV over R, and that's to the negative 1 power. That's to the negative 1 power. Now, what's this CV over R? What's this CV over R all about? CV, let's see here, the relationship between specific heats for an ideal gas, CP minus CV is equal to R. So this guy here, CV over R is actually equal to CV over CP minus CV. CP minus CV is R for an ideal gas. Now I'm going to divide top and bottom by CV, and so I get 1 over CP divided by CV minus 1. CP over CP, ZV is K. I've defined that as K previously in the givens. CP over CV is 1.4. I've defined that in the beginning of the problem. So this guy is equal to 1 over K minus 1. Okay? So this guy, V3, T3 over T, oops, T high and T low. T high, T low. Minus 1 over K minus 1 to the minus 1 power. Let me plug in. Oh, and remember V3 is V max. Yes. Okay, just want to make sure we're consistent here in doing our substitutions. All right, let's plug in V max 0.0254. Yes. Cubic meters. And then I have T low over T high. That's 250 over 300. These both have units of Kelvin, so they cancel out. And then I get minus 1, 1.4 minus 1. And that's to the minus 1 power. And I get the volume at state 2. Volume at state 2 is equal to 0.0161. 0.0161 cubic meters. 0.0161 cubic meters. So now I know V2. So let's go back up here. Let's calculate the heat transfer. Let's see here. The mass, 0.1 kilograms. The gas constant, 0.286 kilojoule per kilogram degree in Kelvin. The temperature T high is 300 degrees Kelvin. And then I got natural log of V2, which I've got 0.0161 cubic meters over V min. V min was 0.01 cubic meters. Cubic meters cancel out. They better for the natural log. The kilograms, Kelvin, and I get kilojoules. That looks good. And that gives me the final heat transfer from the high temperature reservoir of 4.09 kilojoules. 4.09 kilojoules. So Q high, 4.09 kilojoules. Okay? 4.09 kilojoules. 4.09 kilojoules. Okay, let's calculate the efficiency now. Let's calculate the efficiency. So efficiency is equal to the cycle work divided by the heat input. The cycle work is equal to the heat received from the high temperature minus the heat received rejected to the low temperature reservoir. And of course, that's all divided by Q high. And again, we get 1 minus Q low over Q high. Now, Q low is 3.4 kilojoules. And Q high is 4.09 kilojoules. Kilojoules cancel out. Efficiency better be dimensionless. And I get an efficiency of 0.168. 0.168, or if you like, 16.8%. So the efficiency of my Carnot heat engine is 16.8%. So that was the hard way of calculating the efficiency. We actually calculated the heat transfer, QL and QH. There's actually a much easier way to calculate efficiency, for example, a very quick way to calculate efficiency. What is that method? Well, a Carnot heat engine is a reversible device. So note, the efficiency of a Carnot cycle is equal to the efficiency of a reversible heat engine, which is equal to 1 minus TL over TH. Remember where we got this from? 1 minus QL over QH for a reversible process is equal to the ratio of the reservoir temperatures. In our case, we have 250 degrees Kelvin and 300 degrees Kelvin. The Kelvins cancel out. Again, efficiency is dimensionless. And I get an efficiency of 0.168. We're a little bit of rounding going off. Or if you like, 16.8%. Same efficiency, to within a certain level of precision. Okay, there's a lot of rounding going off when we do the more complicated calculation. So the efficiency for a reversible device, heat engine, 1 minus TL over TH, gives us the same exact efficiency as if we actually went through the entire calculation by hand. Okay. Very nice. I think that's it for today. That's a lot of material. Take care, ladies and gentlemen.